Okay, good afternoon, everybody. So last class we were looking at watching this video, TED Talk by Hans Rosling. So let us finish that and then we'll get back to
This
our
is where I
discussion.
realized that there was really a need to communicate, because the data of what's happening in the world and the child health of every country is very well aware. So we did this software which displays it like this. Every bubble here is a country. This country over here is China. And this is India. The size of the bubble is the population. And on this axis here, I put fertility rate. Because my students, what they said when they looked upon the world, and I asked them, what do you really think about the world? Huh? Well, I first discovered that the textbook was Tintin mainly. And they said the world is still we and them. And we is Western world, and them is third world. And what do you mean with Western world? I said, well, that's long life in small family. And third world is short life in large family. So this is what I could display here. I put fertility rate here, number of children per woman, 1, 2, 3, 4, up to about 8 children per woman. We have very good data since 1960 about, on the size of families in all countries. The error margin is narrow. Here I put life expectancy at birth, from 30 years in some countries up to about 70 years. And 1962, there was really a group of countries here that was industrialized countries, and they had small families and long lives. And these were the developing countries. They had large families and they had relatively short lives. Now, what has happened since 1962? We want to see the change. Are the students right? It's still two types of countries? Or have these developing countries got smaller families and they live here? Or have they got longer lives and live up there? Let's see. We stop the world. And this is all UN statistic that has been available. Here we go. Can you see there? It's China. They're moving against better health. They're improving there. All the green Latin American countries, they are moving towards smaller families. The yellow ones here are the Arabic countries, and they get larger families, but longer lives, but not larger families. The Africans are the green down here. They still remain here. This is India. Indonesia is moving on pretty fast. And in the 80s here, you have Bangladesh still among the African countries there. But now Bangladesh, it's a miracle that happens in the 80s. The imams start to promote family planning, and they move up into that corner. And in 90s, we have the terrible HIV epidemic that takes down the life expectancy of the African countries, and all the rest of the world moves up into the corner where we have long lives and small family, and we have a completely new world. Let me make a comparison directly between United States of America and Vietnam. 1964. America had small families and long life. Vietnam had large families and short lives. And this is what happens. The data during the war indicate that even with all the death, there was an improvement of life expectancy. By the end of the year, the family planning started in Vietnam, and they went for smaller families. And the United States up there is getting for longer life, keeping family size. And in the 80s now, they give up communist planning and they go for market economy, and it moves faster even in social life. And today we have in Vietnam the same life expectancy and the same family size here in Vietnam 2003 as in the United States 1974 by the end of the war. I think we all, if we don't look in the data, we underestimate the tremendous change in Asia, which was in social change before we saw the economical change. So let's move over to another way here in which we could display the distribution in the world of the income. This is the world distribution of income of people. $1, $10, or $100 per day. There's no gap between rich and poor any longer. This is a myth. There's a little hump here. But there are people all the way. And if we look where the income ends up, the income, this is 100% of world's annual income. And the richest 20%, they take out of that about 74%. And the poorest 20%, they take about 2%. And this shows that the concept developing countries is extremely doubtful. We sort of think about aid, like these people here giving aid to these people here. But in the middle, we have most of the world population, and they have now 24% of the income. We heard it in other forms. And who are these? Where are the different countries? I can show you Africa. This is Africa. 10% of the world population, most in poverty. This is OECD, the rich country, the country club of the UN. And they are over here on this side, and quite an overlap between Africa and OECD. And this is Latin America. It has everything on this earth, from the poorest to the richest in Latin America. And on top of that, we can put East Europe, we can put East Asia, and we put South Asia. And how did it look like if we go back in time to about 1970? Then there was more of a hump. And we have most who lived in absolute poverty were Asians. The problem in the world was the poverty in Asia. And if I now let the world move forward, you will see that while population increase, there are hundreds of millions in Asia getting out of poverty, and some others get into poverty. And this is the pattern we have today, and the best projection from the World Bank is that this will happen. And we will not have a divided world. We will have most people in the middle. Of course, it's a logarithmic scale here, but our concept of economy is growth with percent. We look upon it as a possibility of percentage increase. If I change these and I take GDP per capita instead of family income, and I turn these individual data into regional data of gross domestic product, and I take the regions down here, the size of the bubble is still the population, and you have the OECD there, and you have sub-Saharan Africa there, and we take off the Arab states there, coming both from Africa and from Asia, and we put them separately, and we can expand this axis, and I can give it a new dimension here by adding the social values there, child survival. Now I have money on that axis, and I have the possibility of children to survive there. In some countries, 99.7% of children survive to 5 years of age, others only 70. And here it seems that there is a gap between OECD, Latin America, East Europe, East Asia, Arab states, South Asia, and Sub-Saharan Africa. The linearity is very strong between child survival and money. But let me split Sub-Saharan Africa. Health is there, and better health is up there. I can go here, and I can split Sub-Saharan Africa into its countries. And when it bursts, the size of each country bubble is the size of the population. Sierra Leone down there, Mauritius up there. Mauritius was the first country to get away with trade barriers, and they could sell their sugar, they could sell their textiles on equal terms as the people in Europe and North America. There's a huge difference between Africa, and Ghana is here in the middle. In Sierra Leone, humanitarian aid. Here in Uganda, development aid. Here, time to invest. There you can go for holiday. It's a tremendous variation within Africa, which we very often make that it's equal everything. I can split South Asia here. India is the big bubble in the middle, but huge difference between Afghanistan and Sri Lanka. And I can split Arab states. How are they? Same climate, same culture, same religion, huge difference. Even between neighbors. Yemen, civil war, United Arab Emirates money, which was quite equally and well used. Not as the myth is. And that includes all the children of the foreign workers who are in the country. Data is often better than you think. Many people say that data is bad. There is an uncertainty margin. But we can see the difference here, Cambodia, Singapore. The differences are much bigger than the weakness of the data. East Europe, Soviet economy for a long time, but they come out after 10 years very, very differently. And there is Latin America. Today we don't have to go to Cuba to find a healthy country in Latin America. Chile will have a lower child mortality than Cuba within some few years from now. And here we have high-income countries in OECD, and we get the whole pattern here of the world, which is more or less like this. And if we look at it, how it looks the world, in 1960, it starts to move, 1960. This is Mao Zedong. He brought health to China. And then he died, and then Deng Xiaoping came and brought money to China and brought them into the mainstream again. And we have seen how countries move in different directions like this. So it's sort of difficult to get an example country which shows the pattern of the world. But I would like to bring you back to about here at 1960. And I would like to compare South Korea, which is this one, with Brazil, which is this one. The label went away for me here. And I would like to compare Uganda, which is there. And I can run it forward like this. And you can see how South Korea is making a very, very fast advancement, whereas Brazil is much slower. And if we move back again here, and we put on trails on them like this, you can see again that the speed of development is very, very different. And the countries are moving more or less in the same rate as money and health. But it seems you can move much faster if you are healthy first than if you are wealthy first. And to show that, you can put on the way of United Arab Emirates. They came from here, a mineral country. They catch all the oil, they got all the money, but health cannot be bought at the supermarket. You have to invest in health. You have to get kids into schooling. You have to train health staff. You have to educate the population. And Sheikh Zayed did that in a fairly good way. And in spite of falling oil prices, he brought this country up here. So we got a much more mainstream appearance of the world, where all countries tend to use their money better than they used in the past. Now, this is more or less if you look at average data of the countries. They are like this. Now, that's dangerous to use average data because there's such a lot of difference within countries. So if I go and look here, we can see that Uganda, that today is where South Korea was 1960. If I split Uganda, there's quite a difference within Uganda. These are the quintiles of Uganda. The richest 20% of Ugandans are there, the poorest are down there. If I split South Africa, it's like this. And if I go down and look at Nigeria, where there was such a terrible famine lastly, it's like this. The 20% poorest of Nigeria is out here, and the 20% richest of South Africa is there, and yet we tend to discuss on what solutions there should be in Africa. Everything in this world exists in Africa. And you can't discuss universal access to HIV for that quintile up here with the same strategy as down here. The improvement of the world must be highly contextualized. And it's not relevant to have it on regional level. We must be much more detailed. We find that students get very excited when they can use this. And even more policymakers and the corporate sectors would like to see how the world is changing. Now, why doesn't this take place? Why are we not using the data we have? We have data in the United Nations, in the national statistical agencies, and in universities and other non-governmental organizations, because the data is hidden down in the databases. And the public is there, and the internet is there, but we have still not used it effectively. All that information we saw changing in the world does not include publicly funded statistics. There are some web pages like this, but they take some nourishment down from the databases, but people put prices on them, stupid passwords and boring statistics. And this won't work. So what is needed? We have the databases. It's not a new database you need. We have wonderful design tools, and more are added up here. So we started a non-profit venture, which we called Linking Data to Design. We call it Gapminder, from London Underground, where they warn you, mind the gap. So we thought Gapminder was appropriate. And we started to write software which could link the data like this. And it wasn't that difficult. It took some person years. And we have produced animations. You can take a data set and put it there. We are liberating UN data. Some few UN organizations, some countries accept that their databases can go out on the world. But what we really need is, of course, a search function. A search function where we can copy the data up to a searchable format and get it out in the world. And what do we hear when we go around? I've done anthropology on the main statistical units. Everyone says it's impossible. This can't be done. Our information is so peculiar and detailed, so that cannot be searched as other can be searched. We cannot give the data free to the students, free to the entrepreneurs of the world. But this is what we would like to see, isn't it? The publicly funded data is down here, and we would like flowers to grow out on the net. And one of the crucial points is to make them searchable, and then people can use the different design tool to animate it there. And I have a pretty good news for you. I have a good news that the present new head of UN Statistics, he doesn't say it's impossible. He only says we can't do it. And that's a quite clever guy. Huh? So we can see a lot happening in data in the coming years. We will be able to look at income distributions in completely new ways. Huh? This is the income distribution of China, 1970. This is the income distribution of the United States, 1970. Almost no overlap. Almost no overlap. And what has happened? What has happened is this, that China is growing, it's not so equal any longer, and it's appearing here, overlooking the United States, almost like a ghost, isn't it? Huh? It's pretty scary. But I think it's very important to have all this information. We need really to see it. And instead of looking at this, I would like to end up by showing the internet users per 1,000. In this software, we access about 500 variables from all the countries quite easily. It takes some time to change for this. But on the axes, you can quite easily get any variable you would like to have. And the thing would be to get up the databases free, to get them searchable, and with a second click to get them into the graphic formats where you can instantly understand them. Now, the statisticians doesn't like it because they say that this will not show the reality. We have to have statistical analytical methods. But this is hypothesis generating. I end now with a world there the internet are coming, the number of internet users are going up like this. This is the GDP per capita, and it's a new technology coming in, but amazingly how well it fits to the economy of the countries. That's why the $100 computer will be so important. But it's a nice tendency. It is as if the world is flattening off, isn't it? These countries are lifting more than the economy. And it will be very interesting to follow this over the year, as I would like you to be able to do with all the publicly funded data. Thank you very much.
Okay, so hope you all liked it. Any comments on what you like about this video? Because it's an excellent demonstration on how you can make a data presentation very interesting, informative. It can be insightful, and it can give you insights about the connections among data. Can somebody explain what they find interesting about it? You can unmute yourself and make some comments. Okay, Shiv Kumar, are you there? Okay, so let me say a few things. So first of all, normally when we talk about data presentation, the simplest data presentation that we all know is a graph, where you plot x against y and draw a line. Right? If it's not possible to draw a line, maybe you'll draw a scatter plot. I mean, these are the kinds of things we began with, right? And then we also showed more complicated kinds of data visualization. But this guy takes that whole effort to a new level. So, for example, if you look at one of the first data presentations that he has shown, there also he started with x and y axis, because in the first one he shows the relation between the fertility rate and life expectancy. So it plots them as a scatter plot, right, between against x and y axis. Then another thing which he adds is he shows many countries, right, on this scatter plot. Now each dot on that plot now indicates a country, and the size of the dot, which becomes a disk, right, indicates the population of that country. So you get more information. So it's not just two quantities, but there's one more quantity added. Then he animates it over the years, right, starting from 1962 to 2000 or something like that. So that gives an idea of how the countries have progressed during that interval. And you can also see the pattern of progression. For example, China, you see that it progresses in leaps and bounds, right? Sometimes it even goes back a little, kind of regresses a little, and then shoots forward in a very short period. All those accelerations and decelerations, you can see when you do a time simulation, right? And in fact, he even has this fast forward option where you can see the whole thing in a faster pace, and you can see all these patterns more clearly, and you can relate those sudden changes, those events in that animation with some government policies. So, for example, they said suddenly in Africa, life expectancy started going down. Why is that? Because of suddenly an outbreak of AIDS, right? The AIDS epidemic. Then, um, yeah. So, and also one thing you might have noticed is that India progress, right, is always very steady. It's somewhat sluggish, but it is steady, and you see that pattern even now. So, and so one more feature that you see there is color, right? You can, the different countries are given different colors. So that I don't remember exactly what color was signifying, but that's another parameter. So thing is, although it's a 2D demonstration, right? He used X and Y, two things, and then the size of the disk, which is population size, then the temporal variation, then time dimension, which is then the fourth dimension, then color, which gives more information. So in one, and so the whole thing is given in such a live and vibrant form with all the features of fast forward and and all that. It gives a lot of information to the viewer. So the thing is, we want to develop this data presentation so that it gives some insight. That's the first thing. Second thing is you want to be able to use it for action, for planning, right? Policymakers use these kinds of data to make decisions. So data must be presented in certain fashion so that it will help the policymakers to make a decision. So that is the objective of the whole data presentation, data visualization, right? So he's done such an excellent job of that. So one more thing you see there is layering. So for example, if you'll see a disk in the display. If you click on the disk explodes into smaller disks, which shows the situation in various, say, parts of the country or various sections of the population of the country. So, for example, he says Gulf. Gulf. This is where where it is located in terms of this X and Y axis, and there's just one big bubble. So, if you split that bubble, it will split into lots of small bubbles, and some bubbles are way high up, and some bubbles are way down below. Right. For example, if you explore the Gulf, right, there is UAE, which is very high up, and there is Yemen, which is very low with civil war and all that. Similarly, he says even in a single country, you'll have huge diversity and huge gap. Like he talks example of Nigeria. So one of the things that he wants to establish in this whole video, in this whole talk, is that there's a lot of prejudice, a lot of preconceived notions about the state of development of different parts of the world, right? And that was a very starting point of this whole talk. And if you look at data, you see it's not that simple, and there's a lot of heterogeneity. Within what you call a backward region, there's a lot of progressive pockets, and also vice versa. Within what you call like a very advanced country, you will find pockets which are very regressive. By the way, how many of you know? So if you look at literacy rate, because I keep tracking literacy data. Say Vietnam, Sri Lanka, India. Who do you think has higher literacy? Right. Or so Sri Lanka and India. Where do you think is higher literacy? Any ideas? Okay. Mohit Kushwa, Sri Lanka. How much? Very good, Navashri. What is India's literacy rate? Current literacy. Roughly. I'm just
74%.
Yes, 77 is what I heard in September last year. There's a news item. So the thing is, the new census data is supposed to come out this year. But before that, the newspapers are writing some articles. Because the thing is, it was 74 in 2011, so it can't be 77. I mean, I'm really surprised. But that's what one Times of India article says in September. So I'm hoping, because India has been, like I said, the progress is steady. It's not great, but it is steady. So which is plus and minus about it. So I was hoping something like 84%, but it is still only 77%. And Sri Lanka, I've seen long ago, it was 90 plus. and now it should be even higher. And Vietnam, same story. China is also in the 90s. So point is, I don't know whether you are also following data or you have preconceived notions. But in terms of literacy, a lot of these small countries, even in South Asia, right, which we think are backward, they actually have very high literacy rates compared to India. Okay, so only people we can compare ourselves with is maybe Afghanistan or even Pakistan. Okay, so anyway, so that's so another nice thing about this talk is at the end of it, he says there's huge amount of data which UN has access to, but if you are able to package it in certain fashion, present it in a creative way. For example, you look at the last picture he showed. He shows all these databases as some kind of a soil, right? And the software which will mine all that data, and that he says that's like roots that goes into that soil, and out of that you have these blossoms coming out, trees and blossoms and fruits coming out, which is like data presentation, data visualization, tools, right? And then you show that data to various sections of people and help people, shape policy. So that's what this company does. He says this Mind Gap or Gap Minders company that he started, right? A non-profit organization. That's what it is. It's a beautiful, line of work. So if some of you are interested in startups and looking for startups, I think this is a great place. And especially in India, there's not so much data getting generated in various domains, and there's a lot of thinking and a lot of think tanks operating in various areas to figure out what is the best policy. And sometimes in the absence of good data, or even when data is present, you don't have the patience and time to analyze the data and do a more careful study. People just come up with very crude policies, which are very hasty and is likely to have a lot of negative repercussions. So there is again that again shows the need for very careful data mining and intelligent presentation, so that your policies will be more optimal. Okay, so I think there's a lot that we can learn out of that single talk. I thought that's a good thing to look at in this context. So now let us go back to our lecture sequence. I'll share this slide. So I think I'll share the entire screen because there was some problem with slide changing. So you can see the slides, Sandeep?
Yes. Yes, sir. Yes.
Data, right? You see that?
Data.
Yeah,
Yes.
okay. So, yeah, so we'll talk about, so we've looked at how do you represent data and how do you visualize data and all that. Now we'll talk about how to compare data, right? And simple ways of comparison and some very basic pre-processing of data. So first thing that you need to know is how do you compare data, or there are two kinds of things for data comparison. One is similarity, another is distance. Both are kind of complementary ideas. Similarity tells you how similar two objects are, distance tells you how dissimilar the two objects are. So the numerical value of similarity tells you how close the two objects are. And usually in the range of 0 to 1. A well-known measure is cosine. So what that means is if you have two vectors, right, cosine will be, so if you have two vectors x and y, so x, okay, x and y are both in Rn, the n-dimensional vectors. So the cosine of right angle of x and y, take that and take a cos of that. Okay, so that is the cosine similarity. So this is nothing but x dot y by norm x times norm y. Okay, so this is between 0 and 1. Or okay, actually it can go even between -1 and 1. Then the dissimilarity, distance. So here Euclidean distance is a standard thing, and I'll come to distance in a second. So if we have a data matrix which represents endpoints, right? So you have each column is a vector, right? So these are n-dimensional vectors. So number of columns is number of rows is n, and number of columns is p. Okay, so you have n points here. Then the dissimilarity matrix will be something like this. So this is of size n by n. Okay, and so since the distance is symmetric, that is d of ij is equal to d of ji. So the distance matrix, which is of size n by n, You don't need to fill the entire matrix. The diagonal terms will be 0, obviously, and it's enough to have only one of the upper triangle or lower triangle to be populated. Okay, so if you take a bunch of points like this, you can calculate, so each of these points, this is an example. The coordinates of each of these points is given, and you can write down the Euclidean distance. So in this case, it's very simple, as you all know. X1 minus x2 whole square plus y1 minus y2 whole square. Okay, square root of the whole thing. We look at a more general measure of distance in a second. So then, when you have nominal attributes, right, that is just a label, right? It's not a numerical value, right? Then how do you calculate distance? So nominal attributes, let us say, can take multiple values, so red, yellow, blue, etc. Then one method is simply matching. So if let's say xi and yi, two components of two vectors, each of them is a nominal value. If red, let's say xi is red and yi is blue, then the two don't match. The ith components don't match. So the distance for this comparison will be 0. Okay, otherwise the match, then the comparison distance for this is if they match, the similarity is 1. If they don't match, similarity is 0. So you count the number of matches. Okay, so m is the number of matches and p is the total number of variables. So then the distance is given as m minus p by p. So that is like 1 minus m by p. So m is some kind of distance, right? And 1 minus m by p is, m is the number of matches, which is some kind of similarity. So whereas 1 minus m by p is a kind of distance. Then sometimes we have a large number of binary attributes. So then you use a different kind of a measure. So if the data object is defined by a large number of binary attributes, and sometimes certain kinds of data, you find that the number of ones and number of zeros are not the same. Okay, so you can have like lots of zeros and only ones showing up here and there. Okay, suppose you have data like this, then simple number of matches may not be optimal, because you'll always have very small number of matches. Let us say it's a 1000-dimensional vector and usually ones are only 20, 30, right? Then if you look at number of matches, you'll always have a low number. It doesn't have much sensitivity. So for that case, there's a slightly different measure. So let us look at that. When the distance measure for symmetric binary variables, that means number of ones. Symmetric means number of ones is roughly same as the number of zeros. Okay, so in that case, life is simple. So how do we do that? So if you have two objects, object I and object j, then both are binary vectors. So for a given bit, right, if you have 1 and 1 on both sides, the number of such matches, let's call it q, and number of occurrences of 0 in object j and 1 in object I, let's call that r. Right, number of occurrences of 1 in object j and 0 in object I, let's call it s, and number of occurrences of 0 in both objects, let's call that t. Okay, so now you can define distance like this. Distance is r plus s by q plus r plus s plus t. What is the logic of this? R and s indicate the number of times where the two bits don't match. Okay, so that is the notion of distance, and that divided by the total number of bits. Q plus r plus s plus t is the total number of bits. That's a measure of distance. Now, thing is, when you have an asymmetric binary variables, that means, let's say the number of zeros is much higher, right? Then what will happen is t will always dominate. So if I have t in the denominator, then this quantity will always look small. So you don't have much sensitivity, right? So therefore, to make the measure more sensitive to differences, people just ignore this t, because t is always a large number, and t is almost as big as the total number of bits. So this kind of for an asymmetric binary vectors, they use a different measure where you have r plus s in the numerator, which indicates the number of mismatches, right? And the q plus r plus s, that is total number of bits minus total number of zeros or 0, 0 matches. Okay, if you do that, and that is called Jaccard distance. Jaccard distance, and the corresponding similarity thing, because R and S together indicate the mismatches, Q and T indicate the matches, but T will ignore because that's mostly it will match, so that's not very informative. So we'll only look at Q as a number of proper matches. So for the just Jaccard similarity, you take Q in the numerator and Q plus R plus as the denominator. And for the Jaccard distance, right? So this is Jaccard distance. It is R plus S in the numerator and Q plus R plus S in the denominator. So just to take a small example, if you want to take Jaccard distance between two objects, this is how you compute distances, right, between objects which have nominal values, which can be expressed in terms of binary variables. So let's say an apple as an object can be expressed in terms of, or to take two fruits, you can express them in terms of these attributes. The shape, that is, then there is the shape spherical. That is the question. That's what this bit indicates. Is it sweet? Is it sour? Is it crunchy? Okay, so then you give binary values to each of them. Apple is roughly spherical, so yes. It is sweet, yes. It is kind of sour, yes. And it is crunchy, yes. Now banana, it is not spherical, it is sweet, it is not sour, it is not crunchy. Okay, so these are all no's are zeros and yeses are ones. So binary representation of apple is this and banana is this. Okay, and it is not actually asymmetric data because ones are also pretty large in number. But suppose I ask, like, give me Jaccard distance, right? Then you have to calculate Q, R, S, and T. Number of Qs, number of 1-1 matches, right, is just 1. Okay, number of R matches is 3. Number of S matches is 0. Number of T's, that 0, 0 matches, there is none. Actually, so the data is not actually asymmetric. But let us say I want to calculate Jaccard distance. It is R plus S by Q plus R plus S. So that is 3 by 4. Then how do you standardize numeric data? Because when you calculate distance, especially if you have a vector in which they're very different quantities. I don't know if you have attributes like, let's say, pH value and temperature, and mass, right? All in one this thing. So pH value could be or some concentration of some chemical. So they're all, let us say, one vector, right? Concentration could be in millimolar, so 10 power minus 3, and pH is in integers between, say, 0 to 14 or something. Temperature is in, let's say, tens or hundreds, depending upon whether you're using Kelvin scale or Celsius. Then mass is, let us say, something else. So the thing is, your numerical values in the vector could take various ranges, very different ranges. So that will mess up your calculation because the absolute range may not be that important. Right, so therefore, to normalize and make all the numbers look in the same numerical value or numerical range, people define something called a Z-score, which where you subtract the mean of the variable, right, from the variable, the sample value, and divide it by sigma. So this subtraction, this taking of the difference, gives you only the variation about the average value, which is more meaningful. And division by standard deviation gives you rescaling. It will give you a normalization so that all numbers will vary over 0, right? And with maybe roughly equally on both sides, positive and negative sides. And the magnitudes of these numbers will all be in the same range, hopefully, right? All between, let's say, small positive number and a small negative number. So mu is the mean and sigma is the standard deviation. Right, and so then you can define different kinds of distances. So one kind of, so there's a very generalized kind of distance called the Minkowski distance. You can also, this is also the basis of something called the LP norm. Okay, so norm and distance are very related. Right, distance between 2 points. Okay, so let me draw it here. If I have 2 points, then you have distance, that is d, ij. This is I, this is j. But if I just have one point and you want to know the distance between that point and the origin, so that is the length, okay, of the vector, and this is the norm, right? So if when you take a distance formula and just set one of the vectors to 0, the origin, then you get the length formula or the norm formula. Now, one property of any distance measure, desirable property, is it should be always positive. Because distance is, you consider it to be a positive quantity, right? And it should be symmetric, right? A to B is equal to B to A. And it should satisfy the triangular inequality. Okay, so that means if I have 3 points ABC, right, and AB plus BC is greater than AC. Okay, so that is the triangular inequality. But so this actually, there are geometries where triangular inequality is not valid, but that follows a different set of laws. So normally when you want a distance measure, it should follow, it should have all these 3 properties, right? When you have a distance measure that satisfies all the 3 properties, it's called a metric. Now, so in this general formula, so what do we have here? Xi minus xj, right, and or xik minus xjk, k for the kth component, right, and power of h, and so sum of that over all the components k, and then take the hth root of this whole expression, that is your LP, so distance, Rabin-Cohen distance, and if you take one of them to be origin, you get LP norm or LP distance, LP length. So if h is equal to 1, the measure will simply look like this, right? xi1 minus xj1 and so on and so forth, right? And if h is equal to 2, you get this sum of squares of different, takes square of each difference and then take a square root of the whole summation. This is what we call Euclidean distance. And same thing if you take h tending to infinity, right, you will get supremum. Okay, so this will pick the highest difference, right? So the final answer will be equal to the highest difference among all these different differences. So let us do a little exercise, at this point, just to give an intuition of what this distance looks like. All right. So let us take a small equation. So x power h plus y power h is equal to c power h. Okay, let us say this is general equation. This is an equation, and so this is of the form f of x comma y is equal to some constant. Okay, c. So now if h equal to 1, so this is a curve, right? F of x y is equal to z is equal to f of x comma y is equal to some constant. So this is a curve. So if h is equal to 1, what will this curve look like? Anybody? So if I want to see, can you unmute yourself and give an answer? Hello, anybody?
So rhombus.
A
Rhombus.
diamond.
Yeah, very good. Okay, perfect. So what happened to my? Okay, my pen is messed up. Just a second, there's some problem with my pen. Yeah, so that's right. So because you're using mod, right, at every quadrant you'll have a straight line like this, and it forms a diamond or rhombus. And now when you go to h equal to 2, anybody? Right, so this is mod x square plus mod y square is equal to constant. Okay, so obviously mod x square is nothing but x square plus y square is equal to some r square. So this is a circle. So you all know this. Now another interesting thing, because what I'm trying to say is like h can be any real number, any positive number. So if you take for example, h equal 2 by 3, you get a very strange curve which looks like this. This is like a real diamond. Have you heard of this curve? Any idea what this curve is called? Anybody? It's called an asteroid because it looks like a star, right? Aster is star, right? And so what reason I want to show you this is there's a very nice book called Straight Lines and Curves. Well, of course, I'm not going to ask you about this book in the exam, but I just want you to, so because when you do data analysis, the foundations of data is in geometry, right? The way you process data, way you understand data, way you represent data in n-dimensional spaces. Right? For all these foundations are in basic geometry. So if you have good geometric intuition, that will be a solid help in understanding data. So there is a book that I've read, in my high school days called Straight Lines and Curves. It gives like a history of various curves that people, grapple with through the history. And so, for example, this cover page picture, it's a very interesting result, very counterintuitive. So if you take a circle, this outer circle, and put a smaller circle inside that of radius half, so that the diameter of the inner circle, right, will go through this inner circle will go through the origin of the outer circle because the radius is half. So now if you roll the inner circle, right, inside the outer circle, then you track the motion of a given point on the inner circle. Can you guess the trajectory of that point? Take any point on the circumference of the inner circle and now roll the inner circle inside the outer circle. Can anybody guess the trajectory of that point?
Some kind of cycloid or something.
It is in general cycloid, but in this case, it's something very simple. That's what is beautiful about this result.
Seems like a straight line from the picture.
Perfect, yeah. It's all in there in the picture, yeah. So it's a straight line. There's a straight line which becomes the diameter of the outer circle, which is very beautiful. And proving it is not that trivial, right? You can kind of, if you have time, you can just go ahead and play with it. Apparently, if I remember right, Copernicus was one of the guys who discovered this result. And so the book is full of such very interesting stories. And really fall in love with geometry if you take the PDF should be available somewhere, right? Just take a look at it if you have time. I'm not going to ask this in the exam, but this is just for fun. Okay, so that is Minkowski distance, which is we have looked at the general formula, and you can also prove for yourself, what happens when the power h goes to infinity. You can show that it picks up the maximum value. Then we define something called ordinal variables. So we have defined ordinal variables, but how do you define distance with ordinal variables? So further, we need to convert the ordinal variable into some kind of a numerical quantity. So how do we do that? It can be discrete or continuous. In ordinal variable, you have a rank, right? So basically convert your ordinal variables into ranks. So 1, 2, 3, 4, like I said, good, better, best. Okay, these are non-numerical quantities, but they have a rank order. So just convert them into 1, 2, 3 or something like that. And once you do that, make sure you start the ranking from 1. Then convert this into another kind of numerical quantity, real number. By applying this formula, RIF minus 1 by MF minus 1, where M is the number of ranks. So once you do that, you've converted your ordinal variables into a vector. Then you can kind of do numerical calculations on that. Okay, so this again shows cosine similarity. Cosine similarity is used for good for very high dimensional data. So where the angular deviation itself is important, but not the length of the vector is not very important. So like I said, you can represent documents as vectors, by in terms of the keywords. Suppose I take a bunch of keywords like team, coach, hockey, baseball, etc., and count the number of occurrences of different keywords in the document. I can represent document as a vector. And usually you end up taking very large number of hundreds of keywords. So you get large vectors with very high dimension. And if you want to compare documents, people usually use cosine similarity, which is just this formula. We already seen that. Okay, and yeah, so we have seen this. That's it, I think. So we have looked at a bunch of distance measures and similarity measures. So with this, now we're in a position to look at start the first major topic of data analysis, which is clustering. Right. So let us start with that from the next class. Maybe next class we'll have next week we'll have tutorial on what we have already covered, but the next topic will be clustering. Okay. Any questions? So chat box, yeah, no questions. Correct. Straight line is correct. Okay. So thanks a lot. See you in the next class. Bye.
Yeah. Thank you.